All right, let's dive in. We're going to tackle a classic problem from a notoriously tough physics book, Irodov. This is problem 1.134, and on the surface, it just looks like a block on a ramp. But trust me, once you master the strategy for this one, you've basically got a key that unlocks a ton of other mechanics problems. So, let's break it down step by step. You know the feeling, right? You see a setup like this, and it looks familiar, but the moment you start wrestling with all the angles and the friction and the different forces, it all just kind of gets tangled up in your head. Well, the goal today is to give you a simple, repeatable playbook that's going to cut right through that confusion every single time. So here's our mission today. We've got a body, mass m, and it's given a shove, an initial velocity v0, straight up a ramp. We know the ramp's angle, alpha, and we know the friction coefficient, k. We need to figure out two things. First, how far up the ramp does it actually travel before it runs out of steam and stops? And second, over that distance, how much work did friction do? Let's get into it. Okay, step one. Before we write down a single equation, before we even think about touching a calculator, we have to draw. This is non-negotiable. We need what's called a free body diagram to map out every single force that is acting on this block. If you get this step right, I promise, the rest of the problem becomes so much clearer. First up, the easy one, gravity. It's the one force that doesn't care about the ramp's angle or anything else. It just pulls the object straight down, always, toward the center of the Earth. And that force is equal to the mass m times g. Next, we have the normal force. Now, normal in physics is just a fancy word for perpendicular. This is the support force from the ramp pushing back on the block, and its defining feature is that it's always at a perfect 90-degree angle to the surface of the ramp itself. And finally, we have friction. So since our block is moving up the ramp, friction is going to do what it always does, oppose the motion. That means the force of kinetic friction is pointing down the ramp parallel to the surface. And that's it. Those are the three forces we have to worry about. So now that we've got our forces all identified and drawn out, it's time to translate this picture into actual math. And the absolute key to making the math simple instead of a nightmare is choosing the right coordinate system. And here it is, probably the single best tip for any problem involving a ramp. Instead of using a standard flat XY grid, just tilt the whole thing. Make your x-axis run parallel to the ramp and your y-axis perpendicular to it. Why? Because the block is only moving along the ramp. By doing this, all the acceleration happens only along our new x-axis, and the acceleration in the y direction is just 0. This simplifies things a lot. Now, tilting the axes is definitely the smart move. But it's exactly at this point that a lot of students walk right into the single most common trap in these kinds of problems. And it has everything to do with that normal force. This is the big one. It's so tempting to say the normal force, N, is just equal to the weight, mg, because on flat ground, that's true. But on an incline, the ramp isn't supporting the block's full weight. It's only pushing back against the component of gravity that's perpendicular to its surface. So N does not equal mg. It equals mg times the cosine of the angle alpha. So how do we find these components? Well, since we tilted our axes, gravity is the one force that's now at a weird angle, so we have to break it down. Using a little bit of simple trigonometry, we can see that the part of gravity that's pulling the block into the ramp is mg cos alpha, and the part that's trying to pull it down along the ramp is mg sine alpha. Okay, the setup is finally complete. We've got our forces, we've broken them down into components, and we've got our slick, tilted axes. Now we can finally apply the most famous law in all of physics to build our equation of motion. The sum of all the forces equals mass times acceleration. We're going to apply this simple, powerful rule to our tilted x-axis, the direction of all the motion. This is where all that careful setup is really going to pay off. So let's just add up the forces along our x-axis. We have that component of gravity pulling it down the ramp. That's negative mg sine of alpha. And we also have friction pulling it down the ramp. So that's negative f sub fr. Those are the only two forces in that direction, and they have to equal ma. Now we also know that the friction force is just the coefficient, k, times the normal force, n. And we already figured out that n is mg cos of alpha. So we just substitute that in, and there it is, our full equation of motion. And now, watch this. When we solve for the acceleration a, notice that the mass m is in every single term. That means we can just cancel it out. This tells us something really cool. A heavy block and a light block would actually slow down at the exact same rate. The acceleration only depends on gravity, the angle, and the friction. And that negative sign out front, that just confirms what we already knew. The block is slowing down, it's decelerating.
Believe it or not, that was the hardest part. We've calculated the acceleration. And because that acceleration is constant, we can now pull out our simple, trusty kinematic equations to find the distance.
So, we need to find the stopping distance, s. Let's see what we know. We know the initial velocity, that's v0. We know the final velocity is 0 because the problem says the body stops. And we just solved for the acceleration, a. Well, it looks like this classic kinematic equation has all the pieces we need. All we have to do is rearrange that kinematic equation to solve for s. We plug in 0 for the final velocity, v0 for the initial velocity, and that whole expression we found for a. And there you have it. That's the first part of our answer, the total distance the body travels up the ramp before it comes to a stop. Now for the second question. What was the work done by that friction force? Well, the definition of work in physics is pretty straightforward. It's just the force that's applied multiplied by the distance over which it's applied. We already know the force of friction is k times mg cos of alpha, and we literally just solved for the distance s. So to find the work, we just multiply those two things together. And that negative sign is really important. It tells us that friction is a force that removes energy from the system. It's working against the motion of the block. So there we have it, our two answers. But honestly, getting the right formulas is only half the battle. The real goal, the thing that will help you in the long run, is to have a reliable strategy, a playbook you can pull out for any problem that looks like this. And this is that playbook. It's just 4 simple steps. 1, draw all your forces. 2, tilt your axes and break down any vectors that don't line up. 3, apply F equals ma. And 4, use your kinematic equations to solve for whatever you're looking for. This method will turn what looks like a confusing mess into a clear path to the solution every single time. Just think about it for a second. What if an object was sliding down a ramp instead of up? Or what if a block was being pulled by a rope at some weird angle? Or what about 2 blocks connected by a pulley over an incline? This exact same 4-step playbook is your starting point for every single one of them. The specific numbers and forces will change, but the fundamental strategy, that stays exactly the same.